Alright, I'm going to have to go through this fast because it's going to be a longer video. These are the bounds you're given. It's rotated about the x-axis. This here's the boundary, x equals e squared. This is y equals ln x. This is the intersection point. And you got to remember your boundaries also. It's rotated around the x-axis, but you have a boundary y equals 0, which will put your boundary there. So when this intersects with the x-axis, that's going to be 1, because ln x will be 0 when x is 1. Alright, setup, I use the disk method. That's the formula. Set up my integral, volume equals pi times the integral of ln x squared, and the boundaries are 1 to e squared. And I use, like the problem said, I started with using IBP. And these were what I set up. These were my parameters. I got u equals ln x, du equals 1 over x, dv equals ln x, and v bar. I didn't want to mix up v's, so that should actually be dv bar. Is going to be another integral, or not an integral, but an antiderivative. I've never done this before, but I don't see why you can't. I treat it as an antiderivative, so there's no constants in my integration. Alright, so right now I'm integrating v bar to find out my first IBP. So v bar equals the integral antiderivative of ln x dx. Had to use integration by parts once again. U equals ln x, dv equals 1, v equals x, du equals 1 over x. Set it up, v bar equals ln x times x minus the integral x over x dx, uv minus v du. Simplifies down into x ln x minus x. Again, no c because it's an antiderivative, not an integral. Now, I have my v bar, and I can plug it in the original integration by parts. So plugging it in, I get v equals ln x, uv, ln x times parentheses x ln x minus x, evaluated from 1 to e squared, minus the integral of 1 to e squared, x ln x minus x in parentheses times 1 over x dx. Everything multiplied by pi because of the original question. This all stays the same. I distributed my 1 over x, got rid of the x before the ln x and the x here. Separated my integral, made it a little easier to solve. Distributed my negative, so I had a plus integral of 1 dx. I still have my ln x here. Then once again, everything's still the same over here. Now I only have one more integral to solve. My 1 dx was evaluated as x on the boundaries from 1 to e squared, and my ln x is now down here. Everything's still multiplied by pi. Up here, once again, we have the equation. We know we're going to need to use another integration by parts here on the ln x dx. Pick u, ln x, du, 1 over x, dv equals 1, v equals x, which we know this will simplify to what we just did, x ln x minus x. Plug that in into our equation. We get v equals pi times all of this, everything we still had, plus our new x ln x minus x, evaluated on the boundaries 1 to e squared. Simplifies down, pretty easy, straightforward from here. There, and it goes all the way simplified down to pi times parentheses 2e squared minus 2. Fairly easy to solve when you have your boundaries and you have everything integrated. For example, ln e squared is just 2, which is an easy boundary to solve, and ln 1 is 0, so that cancels that whole part out when you're doing your second evaluation there. And you know, you get the same thing going on this side over here.